In this video, we are going to begin to look at rotational dynamics. So in the past, we've looked at motion in a translational sense, in that when an object moves from one end to another, every part of that object moves in parallel paths. So in this trampoline example, the person is moving translationally to the right, and the head traces out a parallel path that the feet trace out. But in most cases, we actually have a combination of translational motion with rotation. And so as we move, the entire body may move in a parabolic path, but the body is rotating within that parabolic path. And so what causes this rotation, just like force causes a translational motion, there must be something that causes an angular motion or a rotation, and that angular acceleration is caused by what we call torque. Now, torque is what causes some type of rotation, and it's the result of a force, some force acting along a lever arm or some radius away from an axis of rotation. And so we've experienced this before, and we'll see stuff like this through examples, but the amount of torque depends upon where you exert the force and what direction the force is applied according to the location of the axis of rotation. So we define torque by its magnitude. The magnitude of the torque is equal to the magnitude of the force times the magnitude of the lever arm. We use the Greek letter tau to signify the torque, keeping the Greek theme consistent here. And then we'll use F as the force, L as the lever arm. Now here's what's important though. We have to multiply these two together, and they must be perpendicular to each other. So oftentimes we're going to need to use some trig to get that lever arm that is perpendicular to our force, or find that force that is perpendicular to our lever arm. Either way, the SI units for torque, we do use a Newton meter. Now I know you might think, well wait, a Newton times a meter, that's a force times a distance. Isn't that just work? So shouldn't it be in joules? Well, that is true, but that's when they're in the same direction. So to signify, we call this a Newton meter. We don't use the term joules because it's actually not energy, and we'll get into energy later. Keeping our traditional sign convention when dealing with rotation, we say that torque in the counterclockwise direction, or torque that causes counterclockwise rotation, is denoted as positive. So let's look at an example here. We have our Achilles tendon is attached to the heel, and our joint or our axis of rotation is the ankle joint. And the tendon exerts a force of 790 newtons, and we want to determine the torque, or and we want both the magnitude and direction of this force about the ankle joint. Well, what's important here is to notice that the angle at which we exert this force with the lever arm, or at least the distance from the axis of rotation, well, they're not at 90 degrees. So we need to determine what is the perpendicular lever arm. That's this piece right here. So we need to get that from our triangle, from the fact that this distance is given to us at 3.6 times 10 to the negative second meters, or it's about 3.6 centimeters. And we want to use our trig functions to get that perpendicular lever arm. So we know that cosine of 55 is going to equal our lever arm that we want over the 3.6 centimeters. And so we can find L to be the 3.6 times the cosine of 55, multiply by our force, and we see we have a torque of 15 Newton meters. Now, just like any body that experiences a net force will then accelerate translationally, any body that experiences a net torque will then accelerate rotationally. All right, well, in the opposite side, we can see that if the acceleration is zero, Newton's laws tell us that the sum of the forces is zero. All right, whether it's in the x direction, y direction, or both. And so if the angular acceleration, alpha, is zero, then we can conclude that the net torque is zero. There could be forces causing rotation, there could be torque acting on the object, but the net torque, after all of those are added together, the net torque is zero. So when that happens, we say that the body is in equilibrium. There's two different types of equilibrium. There's translational equilibrium and there is rotational equilibrium. Translational equilibrium is what we did with Newton's laws, in that if the sum of the forces is zero in both the x and the y direction, we say it's in translational equilibrium. The body is either at rest or it's moving at a constant speed in either the x or y or both. Whereas if we have rotational equilibrium, that means the sum of the torque is zero, and therefore we have no rotational acceleration, no angular acceleration. So we are not speeding up the rate at which we're rotating. So we could either be at rest rotationally or rotating at a constant angular velocity. So anytime we come up to some type of equilibrium problem or a torque problem, we need to employ the same reasoning strategy that we had back with forces in Newton's laws. We want to select the object to which the equations and the equilibrium are to be applied. So what object are we concerned with here? We want to draw a free body diagram. That is extremely important, to draw the diagram and see what are all of the external forces acting on the object. Choose a convenient set of x and y axes and resolve all the forces into their components that lie on these axes. Then we want to apply the equations, so that's Newton's second law, and then essentially Newton's second law dealing with rotation, where we have the sum of the torque is going to equal zero in these equilibrium cases, and that will say that the acceleration alpha is equal to zero. Select a convenient axis of rotation, so that way the sum of the torque about this is zero, and then solve the equation for any of your desired unknown quantities. So looking at an example here, we see that we have a diving board, a woman standing on a diving board as pictured here in A, and she has a weight of 530 newtons. So we know that that weight going down here is 530 newtons. She's on the right end of the board that has a length of 3.9 meters. So the total length is 3.9, and we see that we're supported by a fulcrum at 1.4 meters away from the axis of rotation that's all the way on the left, where we have this bolt attached. So we want to find the force that the bolt and the fulcrum exert on the board. So looking at this, we have to identify two things that are happening. We are in static equilibrium or translational equilibrium, and we are also in rotational equilibrium. So if we're in static equilibrium first, we see that all the forces up, which is just F2, must equal all the forces down, which is F1 and the weight. So F1 we're calling the force of the bolt. Now what this does is this sets up an equation that we can relate these three forces. The issue is we don't know F1 or F2. So in our equation we have two unknowns. So then we need to look at, well, let's look at the sum of the torque. And let's look at all the torque that's being caused by these forces. And in order to do that, we need to pick an axis of rotation. And this is where, in the last slide, one of those steps was picking a convenient axis of rotation. Well, what do we mean by convenient? Well, picking one that eliminates one of the forces. So if we pick the bolt as our axis of rotation, F1 is applying no torque to this system. How do we know F1 is applying no torque? Its lever arm is zero. So the force times a lever arm of zero, the torque is zero. So that leaves us with the sum of our torque being just F2 times L2 minus W times LW. All right, where that is the force times its lever arm and the force times its lever arm. And so we can set this equation equal to zero, solve for F2, and we find that F2 is 1480 newtons. Now that we know F2, we can go back to that equation that we mentioned before, saying that the upward forces minus the downward forces has to equal zero, plug in what we have, and we can find our final unknown of the force of the bolt to be 950 newtons. Let's look at one more example here. In this example, we have a bodybuilder holding some dumbbell here, and the arm is horizontal and weighs 31 newtons. Now the weight of this, the weight of the arm is important here because we have to factor that into our rotation. And we have the deltoid muscle can supply a total force of 1840 newtons, and we want to know what is the weight of the heaviest dumbbell that he can hold. All right, well, we're given a couple distances. The length of the arm is 62 centimeters. The distance from the shoulder to the center of gravity of the arm is going to be 28 centimeters. And why it's not at the direct halfway point, we'll talk about that later. And then the distance from the axis of rotation to where the deltoid muscle is actually attached is 15 centimeters. And it's attached at an angle of 13 degrees. Now, we have these two other forces here, the force of the shoulder pushing out on the arm and the force of the shoulder pushing up on the arm. Now, notice those are happening directly at the shoulder at our axis of rotation. So in looking at this, we need to look at the sum of the torque. So it makes sense to let our shoulder joint be the axis of rotation. And so when we do that, when we make this our axis right here, notice those two forces, the SX and SY, disappear because they're not applying any torque. They're at the axis of rotation. No torque is applied. So we have three forces causing torque. We have the weight of the dumbbell, the weight of the arm, and where the muscle is attached. And they all have their respective distances. Now, we say that these ones going down, they cause a clockwise rotation. So we're going to say that those are negative because counterclockwise torque is positive. So the muscle is a positive torque where the other two are negative. If you were to flip those and say that the two weights were positive and the muscle were negative, it's not that big of a deal. It would still work. It's just typically we have counterclockwise rotation being a positive torque. So we have all of their forces times their lever arms. The key here, though, is we're at an angle at 13 degrees. So that lever arm is going to be the 15 centimeters times sine of 13 because we actually want this perpendicular lever arm right here. So we need to use sine to get that piece of our triangle. Plugging in all of our given information after we solve for the weight of the dumbbell, we find that we can get 86.1 newtons. That's the highest weight that we can hold just out there by the force that our deltoid muscle can exert. So in all of these problems, we need to set up our free body diagram, set up the sum of the torque is equal to 0, and then we're good to go. Now keep in mind, this is just in equilibrium situations. We will then get into non-equilibrium states where our sum of the torque is not equal to 0, but for right now, we're just looking at when the sum of the torque is equal to 0.